going to talk about the construction of a cluster stack based on open source technologies. So here at the Mind Lab, we've constructed a cluster, and so we'll just be walking through the technologies that we use to build this cluster. So first, what is a cluster? So one definition would be a group of computers that is able to work together. So often this involves pooling the resources from computers and being able to view that from as a single system. So what can you do with a cluster? Parallel computation is one of the first things that comes to mind. So you can have many computers working on the same job, so distributing the work of a job to multiple computers. You can store large amounts of data. So if you are starting to store data at a very large scale that goes beyond traditional storage techniques, then you can use a cluster to do this. And it's particularly effective when you want to have high throughput read and write from that database or data store, because you can distribute the work of reading and writing across the computers. You may also want to use a cluster if you're hosting many web services or database services, and a single computer can't handle that load. So you typically only want to go down the road of using a cluster if it is necessary. So this might be the case if you are trying to do very computationally intensive tasks. So tasks that may take a very long time, you can distribute the work. Typically, short tasks, the latency involved in distributing the work across a cluster outweighs the gains made by distributing the work. So generally speaking, it's for longer tasks. The longer tasks will have the best gains for moving to a cluster-based system. Big data analytics. So if you have a lot of data and you want to analyze this data, like I said, if you have high throughput of reading or writing, then you may want to use a cluster to distribute the work of both reading and writing and analyzing the data. Load balancing across many computers for a single web service or multiple web services. So if you have a website like Facebook, there's no one computer that could possibly handle that traffic, so you have to balance the load across multiple computers. And also to provide high availability, which means if one computer goes down, crashes for any reason, or the application stops working, then there are other computers to step in and fall back onto. So for us at the Mind Lab, we came up with some requirements, which are that the cluster can be built from commodity computers, which means just standard normal servers that don't have any specialized hardware or anything like that. And so the main reason for that is that they're cheap and they don't require any expert knowledge to run or set up. We wanted to perform big data processing and storage, and also host our web applications. So these two things are often done on separate systems, but we wanted to try and do them on the same system. We wanted something that was easy to set up and maintain, and preferably that had no financial commitments, that we didn't have to continue paying a fee to have it up and running. So our first technology that we're going to look at is Apache Mesos. So Apache Mesos can be thought of as the cluster manager, or Apache Mesos is also kind of equivalent to an operating system. And so it, like an operating system, it handles allocating CPU, memory, and disk to the programs running on it. So it pools the resources of many computers into one collective pool, which then can be drawn from by tasks. Then Mesos will run these tasks and distribute them across the cluster as it chooses. And it also monitors each task just using a simple, seeing if the task is still alive. And so in a way, it's kind of like the accountant for the cluster. So it makes sure that there is enough CPUs to run any task that is proposed, and that and it keeps track of how much is used and how much is free. One of the main benefits of using a system like this is it enables dynamic sharing. So in a manually managed system where you deploy your applications separately yourself, you have no guarantees that one program isn't going to consume all the resources of a computer and would therefore strangle or throttle anything else running on that computer. So, as we can see on the left, if we were to put one of the web apps on the database server, then that web app could, if something went wrong or if it had a lot of traffic, could consume all the resources and starve the database server, which would then affect everything. And so, using Mesos, each application cannot exceed its allocated resources, and nor can it consume any resources allocated to anything else. So that allows us to deploy multiple, confidently deploy multiple applications on the same computers. So to run a program on Mesos, it must be done through a framework. So a framework are kind of like the negotiators, and they communicate with Mesos and are offered resources and can decide whether to accept or decline these resources. If they accept, then they can reply with a task for Mesos to run, and Mesos will go ahead and run that task. Otherwise, the resources are freed up and offered to someone else. And so whenever you want to run something, you have to communicate with the framework, not directly with Mesos. So some examples of these frameworks are three that we use. The first is Marathon. So Marathon runs long-running tasks. So that essentially means tasks you want to never stop. So if a task ever does stop, that when Marathon is running it, then Marathon will restart it and keep it running. It also provides different types of health checks, so you can periodically check the health of your apps using different means. So if it's a web app, you can ping a certain page and make sure that it's loading correctly. And if it ever fails this test too many times, then it will restart it. You can have dependencies on other applications, or have groups of applications that must live together. And it provides different upgrade strategies. So whenever you want to update your application, then the update process is such that the new version is deployed before the old version is shut down, so you have no downtime. Chronos runs periodic tasks. So, for example, if you want to run a database backup every night, so it's the distributed version of cron, if anyone is familiar with that. And so yeah, you set a schedule that can be every week, every day, and it will run what you ask it to. So Spark is a distributed computing framework. So that is what we use to do the big data analytics. And so that is based on MapReduce, which cuts up a task into many different jobs, or cuts up a job into many different tasks, and distributes those tasks across the cluster. And so a single job can consume all of the resources and will take advantage of all of the resources of your entire cluster, or all of the free resources. So there are many other frameworks. These include for running MPI programs, for real-time stream processing, for example, if you wanted to process Twitter data, different database and data store frameworks, genetic algorithm frameworks, and massive scientific computations, so doing matrix and graph operations. So to go into the weeds a little bit, how does it actually work between the framework and the Mesos? So first, the Mesos master will offer some resources to a framework. The framework can then either accept or decline that offer, and if it declines, then those resources are offered to someone else. Otherwise, the framework will reply with a task description. That description is forwarded onto a slave, the appropriate slave, and that slave will launch that task. Once the task is running, then the slave will reply with the task status, and the Mesos master will forward that task status into the framework. And so that task status forwarding is done constantly, so that if anything does ever change, then the framework can act appropriately. So Marathon, I already briefly touched on this. It runs long-running tasks. So to run a task or an application on Marathon, you must send a description, an app description, to the Marathon server. So this description contains the CPU and memory requirements of your application, any additional files that you may need to run the application. So this might be Python scripts, or if it's a Java application, then the command to run to start the task, or the Docker image to run. So you can run Docker images, or you can run just scripts or jars or any program you can run from the command line. And there are many more optional parameters, including, like I mentioned, the health checking, or grouping apps together, or dependencies. So this is what the UI looks like for Marathon. So here I've just taken a few of the apps that we're running, and And so these are the running apps that we've already deployed. And so you can see the resources that they've been allocated, the status. And if we were to click on any of these, we have the option to restart the app or create more instances of it. So you can see on the Docker UI, I just for fun, scaled it to 3 instances. So there's 3 instances of the Docker UI running, and it's being load balanced between those 3 instances. You could also destroy the app or roll back to an older version. Here's an example of the task description. So it's a JSON, and you would post this to the Marathon server using any REST client. So in this case, I'm deploying a Redis server. So I've said it needs 1 CPU and 256 megabytes of memory. And I'm going to use a Docker container, and I'm using the base image Redis. And I've described a little bit of the networking. So Docker is a lightweight virtual machine platform or system. And so when using Docker, you package an application along with all of its dependencies into an image. And that image can be passed around between computers or between developers, and will ideally run exactly the same on all computers, because the Docker platform is universal and will always respond consistently to the same image. So in our case, the Docker solves the problem of managing all the dependencies of applications and programs that we want to run. So instead of installing every dependency on every computer in the cluster, we instead package the dependencies into a Docker image along with the application, and send this around. And so the image even includes an operating system. So that might be your Ubuntu operating system. So it really is self-sufficient and complete. To create one of these images, you need to make a Docker file. And that essentially describes the steps needed to construct or craft this Docker image. So there are a number of different commands you can use to manipulate a Docker image. But you always must start with a base image. So here I'm using the Tomcat base image, and all I'm doing is copying the enricher compiled binaries into the appropriate directory. And that's all I need to do. In other cases, you may need to run install commands, so like a pip install numpy, or you may need to move some files around. But yeah, so once you've made this Docker file, you can use it to build an image, which then you can pass around. So using what we've covered so far, the process for deploying an application would be to create a Docker file. Well, first create your application, then create a Docker file and run Docker build. And you can then test this image locally to make sure that it worked as intended. Then you would push the image to a repository that is accessible to the cluster. So this could be a repository on Docker Hub, or it could be a private local repository. Then you would post that app description that I showed you earlier to the Marathon server. And that would then pass that description, will translate that description into a Mesos task and then pass it to the Mesos master. The Mesos master would then send it to the Mesos slave, which would then download the image from the repository you specified, use the appropriate command to start it, and the appropriate networking, and then you can check the Marathon UI that everything went as planned. So once you've deployed your application, you want to, if in the case of a web application or any service accessible over a port, then you want to route traffic to it. And so HAProxy is a proxy server we use. It's a very lightweight and minimal proxy server. And the main advantage is that you can update the routing configuration without ever stopping or interrupting existing traffic. So we can run this update every minute of the day, and so that the config is always up to date, and it won't interrupt any existing traffic. So when an app is deployed on Marathon, a script updates this configuration file by polling Marathon and parsing out the appropriate information and creating a configuration file from it. Then it will reload that configuration file into the running HAProxy server. And then HAProxy will begin routing traffic, the traffic that you told it to the appropriate slave. And so it gets this information from the Marathon server. So that concludes the web application deployment, and now we'll move on to the big data analytics. And so Apache Spark is a distributed data processing framework. So and it can also be run as a Mesos framework, and so can be run on the same computers, on the same cluster as everything else. And because Mesos does the accounting of the resources, it won't interfere with the running web applications or whatever else you're running. So similarly to Hadoop, it is based on the MapReduce programming model. And Spark is very similar to Hadoop. Its main advantage is that it uses memory more aggressively, and so can result in much faster running times. And so, like all embarrassingly parallel programs, you can reduce the amount of time it takes to run a program very, very significantly. So in addition to just the basic MapReduce primitives like map, filter, reduce, reduce by key, Spark also provides a rich set of libraries for typical data processing operations. So there's 4 of them. There's Spark SQL. So that is used when working with typically column-based data. So that might be CSV files, TSV files, files for which each line has a fixed number of columns. The Spark streaming is for real-time processing of data streams. So, for example, Twitter data, or anything else that may be coming in at a constant rate, and you want to be always up to date. And so this could even just be you can define a stream to be a folder, and any files that are written or copied to that folder are taken as the input of this stream and are immediately processed. mlib is Spark's machine learning library, and it provides a very wide array of machine learning algorithm implementations, as well as matrix representations and basic matrix operations to go along with it. And then there's GraphX, which is for graph processing. And so this provides basic graph representations and basic operations, graph operations. So I will say at this point that I did mention earlier that other framework called Hammer, which did the massive scientific computation. So Spark is based on MapReduce, and that is not a one-size-fits-all model. And so, for example, for iterative algorithms, like a lot of graph algorithms, we have many iterations until you get to some convergence. Then MapReduce isn't as efficient as other models, which these other frameworks may implement instead. So, for example, MPI or the Hammer, which is the scientific computation framework, that they enable communication between tasks, while MapReduce doesn't. So yeah, there are other frameworks which you may want to use. So this is the UI for a Spark application, and so this is doing frequent item set mining, and we can see that I've cut the job up into 1,000 tasks, and so these tasks are essentially queued, and then the worker nodes are taking tasks from that queue, you can think of it, and processing them in parallel, and then writing the results to some location. And so we can see the basic statistics about the tasks we're running. So Spark provides very high level as well as low level operations. And so using the machine learning library, we can use the high level operation k-means.train to train perform k-means clustering. And so in this example, if we've got a file that has each line has some data point with a value and some location, some coordinates, then we can read it using the text file method, do a map which will map each line using a function. So this function parsePoint would be defined by us and would, for example, split by comma and select the first element as the value and the rest of the elements as the coordinates, for example, and then we train the model, and then we can read off the results from that model. And so Spark supports Scala, Java, Python, and recently has added support for R, and can be run by submitting a compiled program or a script, or can be run interactively in Scala, Python, and R using a shell for interactive analytics. So in addition to those 4 official libraries, there are many more. One in particular, which is quite interesting, is Adam, which is a genomics analytics platform. And so this is quite a recent, it's quite a new package, and it does a number of different analyses related to genomics data. There are a number of other machine learning packages which provide algorithms which the MLib official package doesn't provide. So some examples are here on the slide. And I mean, I've just listed here the ones that seems the most relevant, but there are many other more software engineering based packages, or text mining, or yeah, those types of packages. So that covered the data analytics. Now for data storage, we use Hadoop HDFS, which stands for Hadoop Distributed File System. And so a distributed file system is a file system where the data is distributed over many computers. And so each file is cut up into chunks, and each chunk is distributed across computers. And typically these chunks are replicated in case, for redundancy, in case any computer crashes. And it also helps with throughput. So when reading a file, you can read it from 3 different places at once. And similarly for writing, which and so typically disk I/O, so reading and writing data, is one of the bottlenecks of dealing with big data that provides a significant performance increase. So to communicate with HDFS, to read and write data from HDFS, we do this by communicating with the name node, which can be thought of as the master of the HDFS cluster. And so the name node stores the file system metadata. So this would be the directory structure, so the folders and the tree of folders, the names of the files and folders, and on what computers each block of data is stored. And so for each file there will be, say, 100 blocks, and it will know the location of all those blocks. And so we'll be able to point you to the computers that will store the data that you're after. And so this is the UI. And so here I'm showing the directory /tmp, and there's 2 files in here and a folder. And so this is just the web UI. I mean, I can't create files or do any manipulation. I can download the files, but that's all. All of the main operations are done through clients, such as the command line, or Spark has a client, or you can have a client that communicates using Java. So why do we need HDFS, and why did we choose HDFS? So HDFS is designed for big data processing. So there are other distributed file systems that aren't. And so the main advantage with HDFS is that it takes advantage of data locality, which means you send the computation to where the data is located. So if we have a file and it's split up into 100 blocks, then we split our job into 100 blocks and send each of those sub-jobs to the computer that is storing the block that that job is for. And so that minimizes the network traffic, which is another big bottleneck for big data processing. And so so it reduces the amount of communication, the amount of data you have to pass between computers. So to conclude, Mesos pools the resources and does the accounting of all the resources of many computers, and also manages the tasks by forwarding task descriptions onto slaves and performing the task status updates. Mesos frameworks communicate with Mesos and can ask Mesos to run tasks. They get offered resources from the pool, unused resources, and can reply with a task description. Marathon is one of these Mesos frameworks and is designed for long-running tasks. So if any task stops, it's immediately restarted, along with other features that support this this requirement. Docker provides a way to package all of the dependencies of each application so that we don't have to install anything except Docker on the computers of the cluster. Spark is a distributed data processing framework that can be run as a Mesos framework and does MapReduce and provides a lot of very good libraries. Hadoop HDFS is a distributed file system for storing big data that Spark can interact with and efficiently run and is efficient for running computation on. And I've included some links to the resources I've mentioned in the talk. Thank you. Are there any questions?
Hello, I'm Marcin from Cincinnati. I would like to see some tests how with certain data sets or computational problems, how you were able to speed up your environments, all those computationals. And other thing, have you tried some hybrid environments? So some of bare metal machines, some virtual machines, and maybe some cloud machines from Amazon or Azure to work together in this kind of setup?
Yeah, so that's a good question. So the second point, I know it is possible to set up a hybrid environment. And Mesos supports labeling your slaves, and so you can label the bare metal slaves as bare metal and the virtual slaves or the cloud slaves as cloud, and then you can constrain tasks to certain labels. So say you wanted your web apps all running on your bare metal or on the cloud alternatively, then then you can constrain to that. For the speed ups, so I'm not quite sure what you're asking. So do you want like some metrics of how much faster it is, or
Yeah, some kind. That will be like good addition for your presentation, like future to like develop the work furthermore, so you can show how good it is.
Right. So essentially, it's how many CPUs you have, and so that becomes kind of the factor of your speed up. So say we're using 150 CPUs, then you could say it's going to be 150 times faster minus some overhead, which may be, I'm really not sure, but it could perhaps be 10 or 20%. So you could end up with, say, like 130, 120 times speed up. So I wonder if this is still running. Yes, it is still running. So we can have a look, and we can say the total time across all tasks is 100 hours, and in real time it's actually only taken 3.8 hours, and so so this is the total CPU time spent on this job. So, I mean, you can run things that go up into very high numbers of total time if you have a lot of CPUs.
Okay, thank you.
Okay, well, thank you, Matthew. If there are no more questions, we'll conclude this. All right, thank you, everybody.